Hello everybody, my name is Tommy Boland and I'm a Professor of Ruminant Nutrition and Sheep Production in University College Dublin. Today I'm going to be talking to you about reducing methane from the agricultural sector, particularly looking at emerging technologies for dealing with enteric methane emissions. If you have questions that are not dealt with fully in this presentation, feel free to email me at my email address located here, or you can also follow me on Twitter to hear more about the research work we're conducting in University College Dublin in this topic. If we move on now to look at the challenges that are facing us in Ireland around greenhouse gas emissions, this slide presents the most up-to-date data we have on Ireland's total greenhouse gas emissions. We're rather unique in Europe, in Ireland, insofar as agriculture contributes 34% of our total greenhouse gas emissions. If we look at the EU 28, on average, agriculture's contribution to greenhouse gas emissions is around 10%, but this figure is substantially higher in Ireland at 34%. The country which would be closest to us globally with a similar figure would be New Zealand, and we have a few things in common with New Zealand, giving rise to this high contribution of agriculture to national greenhouse gas emissions. Firstly, we have a relatively small human population. Secondly, compared to our human population, we have a large ruminant population in Ireland. And finally, we have a relative absence of heavy industry, which could give rise to carbon dioxide emissions. That results in a situation where agriculture accounts for 34% of our total national greenhouse gas emissions. Of these agriculturally derived greenhouse gas emissions, enteric methane, or methane produced from cows and sheep, accounts for about 56% of our total agricultural emissions, placing a huge importance and a huge focus on this particular source of greenhouse gases at a national level. If we move on now to look at how and why methane is produced, we can see that enteric methane, or methane produced in the digestive tract of cows and sheep, is a natural byproduct of the digestion that takes place in the cow's stomach. The cow and sheep have a unique digestive system whereby there is a large microbial population located in the rumen. And this microbial population gives huge advantages to cows and sheep. One major advantage of this microbial population is that it allows cows and sheep to break down carbohydrates, which we find in feeds like grass and silage and hay, which are not able to be broken down by monogastrics or pigs or humans, for example. However, as a byproduct of this microbial digestion taking place in the rumen, methane is produced. And methane is important because, firstly, it's a greenhouse gas, and secondly, in the current accounting methodologies used, methane has a global warming potential which is 28 times greater than carbon dioxide. Global warming potential refers to the impact a particular gas has on the atmosphere over a 100-year time horizon. Now, recently, there has been some debate about how methane is compared to carbon dioxide, and we'll move on to look at why this debate has arisen. Firstly, if we focus on the cow on the right-hand side of this graph, methane, as I've said, is produced as a result of microbial action in the digestive system of our cows. Methane contains carbon. The carbon that's released from the cows in methane is consumed in the feed that the cows consume. So it's consumed in the grass which our cows consume. The carbon in the grass has been harvested or captured from the carbon dioxide present in the atmosphere. So when cows belch out methane, this carbon that's contained in the methane is part of the natural carbon cycle. If we compare carbon dioxide then, on the other hand, which is released when we burn fossil fuels, for example in our diesel engines or to generate heat for our homes, this carbon dioxide has been stored in the ground for millions and millions of years. So when we burn fossil fuels to release energy, we also release carbon dioxide to the atmosphere, which has been isolated from the natural carbon cycle for millions and millions of years. Okay, so moving on then to look at the changes in the Irish cattle population output and how methane has evolved over recent years. We can see from this slide here that over the last 10 years, from 2008 up until 2018, there has been quite a lot of change in the Irish national cattle populations. The total cattle population has changed by about 3%, but that doesn't tell the story. Our dairy cow population has increased by approximately 27%. At the same time, our beef cow or our suckler population has decreased by almost 12%. However, the total milk output nationally has increased by over 50%, and the total beef output nationally has increased by over 19%. These increases in output have been achieved at the same time as enteric fermentation has increased by approximately 10%. So this tells us that the efficiency with which we produce our products in Ireland has improved. And at the same time as these changes in agricultural output have been taking place, the value of agri-food exports has increased by almost 66%. If you can recall, 2008 was just around the time while once again the agri-food industry became the engine that drove the economic recovery in Ireland. So it's important not to overlook the very substantial economical contribution agriculture plays nationally. Moving on, we can see that despite these efficiency gains we have made, there are still greenhouse gas reduction targets as part of the government's climate action plan. So by the year 2030, agriculture is targeted to reduce its greenhouse gas emissions between 10 to 15%. At the same time as these targets for greenhouse gas reductions have been set, there is also a growing consideration internationally that we need to look at methane and carbon dioxide in different manners because they are two different gases which behave differently in the atmosphere. So what I want to do next is discuss some of the options that we have for reducing methane emissions. Before we get into discussing these reduction options, I just want to highlight how and why methane is produced again. Methane production by ruminants is a function of the animal, the diet, and the microbial population present in the rumen. While there is a huge amount of research taking place internationally looking at the microbial population in the rumen, the on-farm applicability of much of this research is still a few years off. So for the next 10 minutes or so, I'm going to focus on the options we have from changing the animal type and from changing the diet type to reduce enteric methane emissions. So how can we actually reduce methane emissions? Well, at the moment, enteric methane production is inevitable, so we'll never fully eliminate it, but we can reduce it. Animals vary in the quantity of methane they produce. So the fact that animals vary in the quantity of methane they produce allows us to select animals for reduced methane emissions. Just in the same way we can select dairy cows for higher or lower levels of milk production, or we can select beef animals to grow faster. We can, in theory, select animals to produce less methane. Now, the problem with this selection is it's very, very expensive and very, very time consuming to measure methane emissions on a large number of animals. And that's what we need to do before we can select animals with higher or lower methane emission levels. New Zealand have made some progress in selecting sheep for reduced methane emissions, and Donnaberry of Teagasc has a large project called Green Breed running nationally, which is targeting the selection of animals, of beef cattle in particular, with reduced enteric methane emissions. Where most of the information has been generated and where most of the research has been conducted in recent years has been looking at different feeds. And we know that different feeds will result in different levels of methane emissions. So by doing things like changing and improving the forage quality, by changing the quantity and type of concentrates we feed to our animals, and by including certain feed additives in the diet, we can reduce methane emissions from our ruminants. So now I just want to look at some of these strategies in a little bit more detail. First, and perhaps the country which has made the most progress in selecting and breeding animals to reduce methane emissions is New Zealand, where they have focused on their sheep population. And over the course of the last 10 to 15 years, New Zealand have successfully bred high and low methane emitting lines of sheep. And there's a consistent difference in the quantities of methane these animals produce, whereby the animals which have been selected for low methane emissions produce 10% less methane during their life and per day than the animals which are higher producing. But in Ireland, the sheep population has declined in importance over the last 20 to 25 years. So our main focus in Ireland is on cattle. And this is where the Green Breed project on the next slide has really come into play. As I said, this project is led by Professor Donnaberry in Teagasc Moore Park. in conjunction with a number of other research institutions around Ireland, including UCD. And they have put infrastructure in place in the ICBF test centre in Tully, which is identifying animals for lower methane emission levels, with the objective of building methane emission breeding goals and breeding values into the National Selection Index over the coming years. At the same time, a lot of detailed work is taking place to ensure that these animals do not have any negative side effects from reduced meat eating quality or reduced animal health outcomes. But a lot of the breeding work is still in its infancy. Moving on, we can see that the dietary interventions have made a lot more progress and been subject to a lot more intensive research. In Ireland, the majority of our animals spend some, if not most, of their life grazing grass. And so we, in our research, have looked at the impact of grass quality on enteric methane emissions by both dairy cattle and sheep and beef cattle. When we look at the impact of change in the quality of grass on the methane output of our dairy cattle, work carried out by Cathal Wims in Moore Park back in 2010 showed that when we fed animals low pre-grazing herbage mass grass, so this is grass of about 1,100 kilograms of dry matter of a pre-grazing herbage mass, their methane output per day was reduced by 13%, and their methane output per kilogram of milk solids or per kilogram of product was reduced by 18%. So why am I using these two different metrics to describe methane production? Well, methane output per day is the value that's included in the national inventories. Now, many of us involved in research would argue that this is not the best metric to use to quantify methane emissions, and we would much prefer to see methane output per kilogram of milk solids being used, because that indicates the efficiency and the emissions intensity of the products we produce. Similar work, moving on, was conducted with beef cattle by my group in Lyons. And we can see here that when we fed high and low quality grass to our beef animals, the animals consuming the grass with a low pre-grazing herbage mass, they reduced their methane output per day by 7%, while the animals grazing the low pre-grazing herbage mass grass reduced their methane output per kilogram of average daily gain by 22%. So similar to what we saw in the dairy cows, we could improve the efficiency of performance of the animals, and we could reduce the daily methane output by improving the quality of the grass we offered to our grazing livestock. If we move on then to look at some options from a supplementation point of view, quite frequently our animals will receive concentrate supplementation, particularly grazing dairy cows at pasture. And one of the additives that has shown quite a lot of potential in terms of reducing emissions are oils or fats included in the diet. Some additional work we carried out at UCD Lyons Research Farm by feeding linseed oil at approximately 4% of the dietary dry matter intake, so that we could reduce methane emissions per day by 17% and methane emissions per kilogram of milk solids by 20%. So again, this is an option, a mitigation option, which could be put in place on many farms around the country to reduce enteric methane emissions from our animals. The major challenge with the three options I have just outlined is that as of yet, the inventory is not capable of capturing these methane mitigation strategies. So even though farmers can apply them, and many farmers are applying some of these strategies, they cannot get credit for them with the way the inventory is currently constructed. And that's something we need to continue to discuss with our policymakers. Moving on then to look at some of the options for finishing beef cattle. And again, what I'm going to present here is just simply focused on methane output per day. It's not looking at the economics of the system or the total carbon footprint of the system. But if we compare two beef cattle finishing systems, as Emma McGough did in Teagasc and Grange in 2010, comparing a finishing diet based on grass silage or a finishing diet which is based on an all-concentrate finishing system, methane output per day was reduced by 42%, and methane output per kilogram of carcass gain was reduced by 60%. Now, I am not recommending that we should be replacing forages in the diet with concentrates as a broad brush approach in our national industry. This simply shows that we can change the level of methane output by changing the diet. What we need to be very conscious of with a strategy like this is A, the marketing of our product, B, the cost of the finishing system, and C, what impact such a strategy has on the overall carbon footprint of our animal production systems. Finally, then I will finish up looking at some of the newer additives which have come on the market. And there's been a lot of excitement in the press and amongst various policymakers about some of these products. In the interest of full declaration, I have no allegiance to any of the companies who produce these products, and I have not worked on the development of any of these products. My experience is based on the published literature. But DSM have produced a product which is known as 3-NOP. It's marketed as Bovair, which has shown quite substantial methane reduction responses when it's fed to ruminants. And a lot of the work is focused on dairy cows, and a lot of the work is focused on dairy cows in indoor house systems. So when this product was fed as part of a TMR or a total mixed ration, methane emissions per day were reduced by 27%, and methane emissions per kilogram of milk were reduced by 24%. Now, we all know that TMR rations to dairy cows would not be the most common feeding approach utilised in Ireland. They had also conducted some work in this study where they were looking at feeding this supplement in the parlour morning and evening to dairy cows. And in that approach, methane emissions per day were reduced by 23%, and methane emissions per kilogram of milk were reduced by 24%. There is an absence of work in the published literature as to what impact this supplement will have on pasture-fed animals, even though there is work ongoing in New Zealand at the moment to try quantify this. But as of yet, we need to be very cautious of the widespread adaptation of any mitigation technology until it's proven within the system we want to apply it in. The next additive I'm going to speak about, which is currently available on the market in Ireland, is a product called Agolin. And this is available through Glanbia as part of their game feeds range. And a recent study, or a recent survey of a number of studies conducted using Agolin has shown that methane output per day can be reduced by 9%, and methane output per kilogram of milk can be reduced by 10% by feeding this product. And in those studies, there was an associated increase in milk yield of 4% and an associated increase in feed efficiency of also 4%. So not only is there a saving from a methane point of view, there is positive impacts on animal performance in addition to the impacts on methane emissions. Finally, then, I want to talk about seaweed. Seaweed has been the focus of a huge amount of commentary and a huge amount of publication in the popular press and in the farming press in the last 18 months. And in some of the studies conducted with seaweed, we have seen quite substantial reductions in enteric methane emissions. The first thing we need to be conscious of is that there are a wide range of seaweeds, and not all seaweeds will generate the same response or even generate any response in terms of methane reduction. So the particular family of seaweeds which have shown benefits are the Asparagopsis family. In some work carried out in the US with lactating dairy cows, just published, methane output per day was reduced by 67%, and methane output per kilogram of milk was reduced by 43% when a supplement of Asparagopsis was offered to the animals. Now, I mentioned earlier, we need to be conscious that we don't have negative impacts on any other aspect of animal production when using these mitigation approaches. In this particular study, feed intake was reduced by 38% and milk yield was reduced by 12%. So neither of those outcomes are desirable, even where we're seeing large reductions in methane emissions. The other interesting thing about the seaweed, and I've said that different seaweeds function in different ways, and different animals appear to respond to to seaweed supplementation in different ways. Some work carried out by Nigel Tompkins and his colleagues in CSIRO, where a lot of this new seaweed data has been generated, looked at a different type of seaweed, Asparagopsis taxiformis, and feeding it to Brangus cattle, a breed or a crossbreed we wouldn't be familiar with in this part of the world, but it's Aberdeen Angus crossed with Brahma cattle. In this particular study, methane output per day was reduced by a massive 98%. However, as methane output was reduced by 98%, hydrogen output per day was increased by 1700%. So hydrogen production is a normal part of what happens in the rumen, and usually this hydrogen is utilized to produce methane, because if the hydrogen builds up in the rumen, it can have negative impacts on animal health. However, in this case, it seems that the hydrogen was being released directly to the atmosphere. We don't know yet what long-term impacts this will have either on animal health or any other aspect of animal performance. Interestingly, again, in this work using the seaweed supplementation, average daily gain of the animals was increased by 22%, and feed conversion efficiency was increased by 26%. So once again, highlighting animal performance benefits. At this stage, it is still way too early to say what impact these seaweed supplementation approaches might have in a pasture-based system of production. But given the level of methane reduction responses we're seeing, it certainly merits some further investigation. So in summary then, I think it's clear that we can reduce methane emissions both through breeding and through feeding approaches. What is also clear is that we must not negatively impact animal health, performance, or efficiency in doing so. Similarly, we must not increase other emissions or reduce the economic viability in our quest to reduce methane emissions. And in order to get credit for these reductions, they must be captured in the national inventory. And this presents a particular challenge for us in our pasture-based production systems, where something as simple as improving the quality of the grass we offer to our animals will reduce the quantity of methane these animals produce. But at the moment, we cannot capture that response in our national inventory. So with that, I thank you for your attention. My email address was available on the first page of this presentation. So if there are questions or areas I haven't covered in this presentation, I would be delighted to deal with them through email. Thank you.